Welcome to the lecture video series for college algebra at Wayland Baptist University. My name is Dr. Scott Franklin and I'll be leading these lectures. I want to begin by introducing the course to you. This college algebra course covers the last half of the Blitzer textbook, 5th edition. Is also being used with the 4th edition as well. But in college algebra, what we're going to be doing throughout the semester is looking at a series of different types of functions that we can use to model real-world phenomena. That is, we're going to be doing a lot of problem solving in order to make use of a series of functions, including rational functions, radical functions, quadratic functions, conic sections, and sequences and series. Because it is college algebra, there is some prerequisite algebra knowledge that is expected from its students. In order to be able to take this class, you need to be familiar with several things, including solving linear equations and being able to work with polynomial functions, polynomial equations, and just polynomial expressions. We are going to do a quick review at the beginning here in Chapter 5 of the polynomial functions, what they are, how we add, subtract, multiply, and divide them, and then how we factor them and use them to solve, or how we solve equations that involve them. Now, we have another course that is a lower level than college algebra for students that have not had algebra in a long time or may not have had algebra at all. This should not be your first algebra class because you are expected to know some algebra coming in. It's college algebra. So high school algebra is something that you should know. We offer Math 1300, Intermediate Algebra, which covers the first half of the textbook. You might consider taking that if you have no clue what I mean when I say a polynomial. It may have been a while, so if you have seen it and you can go through this Chapter 5 review here at the beginning and catch up with what you may have missed, then you may be in fine shape to take this class. But if you're completely lost because I cover things too quickly in Chapter 5, you might want to reconsider taking our intermediate algebra class. So to begin with, let's start with Chapter 5. Let's do a review of polynomial functions, what they are, how we do our basic operations with them, including factoring, and then how we solve equations that involve polynomial functions. To begin our introduction to polynomial functions, let's start by defining what a polynomial actually is. By definition, a polynomial is going to be a finite sum of terms in which all the variables have a whole number exponent and no variable appears in the denominator. So we're limiting ourselves to functions that follow nice rules. That is, if I can spell denominator while I'm talking, denominator, sorry. We're going to limit ourselves to functions that are finite sum of terms, meaning there's a total number of terms there. It doesn't go on forever. The variables have whole number exponents, that is 1, 2, 3, 4, and so on. And the variable is never in a denominator. So you got two things that happen here. You got no variables in the denominator. The second thing you have is that no variables are in radicals. Now the reason that that's true here, the reason why it's not under a radical, goes back to the reason that there are whole number exponents. It turns out, and we will learn this later in this semester, that fractions in your exponent, or decimal numbers in your exponent, actually mean that they are some kind of root or radical. Radical being like a square root or cube root or something to that effect. If you have a variable underneath there, it's not going to be a polynomial. So, looking down in your notes, let's take a look at the next section and identify which of these are polynomials and which are not. Part A of this example, we're asked to identify whether or not it's a polynomial. This one has all whole number exponents, no variables are in radicals, no variables are in the denominator, so yes, that is in fact a polynomial. On part B, you recognize that because of the radical that you see in there, that is not a polynomial. On part C, we have different variables. You notice in A and B we only had a single variable. We had x. Well, it's possible to have polynomials that have more than one variable. That's not a limiting aspect of that definition. And if you look at all the exponents, which looking at this x right here, I don't know if you'll remember this or not, so I'll point it out. Whenever you see a variable without an exponent, it is understood to be 1, right? So x to the first is the same thing as just writing x. So clearly that is a whole number exponent. So is the 3. X, y, and z all have exponents of 1. So yes, indeed, that is a polynomial. It does not violate either of our restrictions. Next. This one right here is another example of a polynomial. Everything is fine and dandy. No variables in the denominator, all whole number exponents. Now this one right here, notice the variable in the denominator, which means this is not a polynomial. What about this one? F. Okay, we have just a single number. There are no variables involved at all. Well, that actually is also considered a polynomial. Finite sum of terms, all the variables have whole number exponents. There are no variables, so it doesn't violate that criteria. And of course, there are no variables underneath radicals. This one right here, because of the fractional exponent, is also not going to be a polynomial. So again, let me emphasize the reason why we limit ourselves to these types of functions is they're nice. We're going to learn how to handle these things inside and out, how to do whatever we want to do with polynomials. And then when we get to more advanced functions, as we go throughout college algebra, we're going to allow ourselves to consider, okay, what happens if we have variables in the denominator? What happens if we have radicals? And what we will typically do is take those types of problems and reduce them down into polynomial problems. Do some sort of trick that gets rid of the mess and turns it into something that we're able to work with. Now that we know what a polynomial is, the next thing we want to be able to do is to do all of our basic operations on polynomials. We want to be able to add, subtract, multiply, and divide. In terms of adding, the basic thing that you need to remember, 3 words. We're going to combine like terms. All right, that means same variable with the same exponents. Those are like terms. So in this example here, we're going to want to simplify this expression by combining the two, combining all of the like terms that we have. So the first thing we do is identify, well, I can just drop the parentheses here because there's nothing inside the parentheses that I can simplify further. All right, so this would be x squared plus 6x plus 4 plus 3x minus 1. Now we're looking for like terms. Two different terms, those things that are separated by pluses and minuses that have the same variables with the same exponents. Now to begin with, looking at this x term, the x squared term, notice there is nothing else like that, so I'm simply going to write down x squared. Now in terms of x terms, I have two different terms, this one and this one, that both have just x's, so what I will do is combine or add their coefficients, the number that is out in front. 6x plus 3x gives me 9x, and then lastly I can say, well, I've got two numbers here, positive 4 and negative 1, that I need to combine. Those are both just numbers, so 4 minus 1 is a plus 3. That is the result of adding those two together. Alright, now on the next problem we have a similar issue except that it's subtracting, and it turns out that there really is no such thing as subtraction, or at least we don't have to think of subtraction as a completely separate operation. Subtraction is just addition in disguise, right? If you're going to add two numbers, well, you know how to add. If you're going to subtract, that's the same thing as adding a negative of the number, right? 3 minus 2 is the same thing as 3 plus a negative 2, right? Okay, so what we're going to do here is to add these together, or actually subtract them. The thing that you have to remember is to take this minus sign and distribute it to each term inside. You're going to subtract this whole polynomial. This is in effect just like having a minus 1 sitting out in front, and whenever you have a number out in front of parentheses, you will distribute that number to each term inside. Okay? So when I multiply that out, here's what I get. Of course, the first polynomial doesn't change. It's still x squared plus 6x plus 4. Now subtracting, I'm going to take minus times 3x. That makes a minus 3x. I'm going to take a minus times a minus 1. That gives me a plus 1. So the thing that you have to remember, one of the easiest things to forget, is when subtracting, always, always, always distribute the negative. Now, I can't do this in my online class here, but something I always do in my traditional classes is I make them chant this over and over and over again. Say it with enthusiasm, say it at the top of their lungs, say, when subtracting, always, always, always distribute the negative, because it's so easy to forget. If you don't do it, right, if I just drop the parentheses, I get this sign right here wrong. That plus is wrong, right? I would just have had a minus, but if I distribute it, I get a plus. Now we go back and do the same thing we did before. We see again that we have this x squared here is the only x squared term, so I have just an x squared. I have two x terms. I have a 6x and I have a minus 3x, so that's plus 3x. And then I have the 4 and the minus 1, or actually plus 1 now, giving me plus 5. And that is that function simplified. That subtraction problem simplified. So we've added polynomials together. We've subtracted them now. The next operation we want to consider is how do we multiply. The rule you learn for multiplying is basically just distribution. You already know, and we've done an example because we distributed the minus sign, that if you have a number like a 3 out in front of something like x plus 2, just a single term out in front, you will distribute that to each term inside, right? And that simplifies to 3x plus 6. Now, if you have more than one term out in front, you actually have two, the rule that you use there is to distribute the first term to each term in the second. Each term of the first polynomial distributes to each term of the second. So in this case it looks like this. I would take the first times the first, right, and get x squared. I'd take the first times that last one right there, and I get plus 4x, and then I do the inside. Okay, that is the 6 times the x, so plus 6x, and then the last together, 6 times 4 is plus 24. Okay, now you'll recognize this. Some of you who've seen this kind of operation done before, hopefully most of you have seen this, you may have referred to it as FOIL, which stands for first, outside, inside, last, because that's the pattern that you see. You do the first together, the outside, the inside, last. Now let me tell you, whenever I first learned this in, I guess it was in like the 8th grade or something, whenever I was first taught how to do this, I never learned FOIL. In fact, I didn't learn the name FOIL until I got to college, and I was tutoring somebody in college algebra, and I was explaining to them how to multiply this out, and they said, oh, you mean FOIL? And I was like, FOIL? What in the world are you talking about? And they said, no, this, whenever you do the first, the outside, the inside, and the last. And I said, oh, you mean the monkey face? The monkey face, they said. What are you talking about, the monkey face? I said, look at it. This is what my teacher called it. You got the mouth here, the chin, the eyebrows, you got the eyes, the big old ears on the side. It's called the monkey face. And so sometimes I will slip in the way that I present this into my college algebra classes. If I ever use the term monkey face as a verb, what I'm saying is to FOIL. That is to multiply out by distributing each term in the first to each term in the second. When it's a binomial times a binomial, monkey face is the shape that you get. And by the way, let me say FOIL only really is relevant if it's binomial 2 terms times a binomial 2 terms. If it's like, say for example, this next one, we're still going to do the same rule of each term in the first distributed each term in the second. We're going to end up with something that doesn't look like a monkey face, for one, but also first and outside, inside. We've got more than just one outside, inside type of thing going on. Right, look at this. So if I take x squared times 3x, I'll get a 3x cubed. Now I got to take x squared times this one over here, which is going to give me a minus x squared. Now I got to take the middle term and distribute it. So I'm going to take it times 3x, which gives me plus 9x. Take this times the last one, which gives me a minus 3x. And now I've got to take the 1 times everything. 1 times 3x is plus 3x. And 1 times, by the way, this should have been 9x squared. I forgot to write that. My apologies. So I've got 1 times 3x is 3x, and 1 times a minus 1 is minus 1. Right? So now I come back in and combine like terms. So I'll have a 3x cubed. Right? That one's taken care of. Combine these two. I have minus x squared plus 9x squared is going to be a plus 8x squared. Add these together. Minus 3x plus 3x completely cancel each other out, and then minus 1, and that is as simplified as I can get it, and there we go. That's done. The last operation that we could consider is division, but we're going to omit that now because we don't really need it for Chapter 6, and in fact we're going to cover a little bit of division in Chapter 6. So let me leave that out for now and move on to the next topic. Ready to tackle the issue of factoring. Now, factoring for a polynomial means breaking a polynomial down into two simpler polynomials that multiply together. In fact, sometimes it may be more than two, but breaking it down into polynomials that are simpler than the original polynomial that multiply together to give me the larger polynomial. It's analogous to what we do with numbers when we factor them into their prime factor, something we will actually need to do later in the semester, but just as an illustration, if I gave you the number, say 36, I can break that down, factor it if you will, into two things that multiply together to give me 36. Now there's a lot of choices here, but one example would be 4 and 9. 4 times 9 is 36, and then I can break each one of those down further into things that are multiplied together. Eventually I'll get to where I can't break them down any further. 2 is just 1 times 2, so I can't go any further than that. And so I've factored the 36 into the simplest type of numbers that multiply together. They're called prime numbers because they're only divisible by themselves in 1. But you've broken it down into prime numbers that multiply together to give you the original number. Well, we're going to take polynomials and do the same thing. We want to break them down into simpler polynomials multiplied together. Okay, so I'm going to give you the step-by-step procedure. The first thing you do before you do anything else in factoring a polynomial is something called pulling out the GCF, the greatest common factor. So we search through here and we find what do they have in common that I can divide out of every single term. So first I look at the numbers 6, 2, and 12 and say, okay, I can take a 2 out of every single one of those. Then I look at the x's and I see, okay, out of those x's, what is the largest number of x's that I can pull out of those? I can't pull out 3 of them because this one, the second term, only has 2. I can't pull out 2 because the last one only has 1. But they all have at least one x. So x to the first power I can pull out. I cannot pull out a y because they don't all have a y. That would be my GCF. Then what I do when I factor it out is if I divide that out of each term, what is left behind? That is, what is it would be in here so that if I were to multiply 2x times every term, I get the polynomial that I started with. So, pull a 2x out of 6x cubed, I'm left with a 3 and an x squared, because 6 divided by 2 is 3, x cubed divided by x is x squared. That's what's left behind when I divide out 2x. On the next one, if I pull the 2 out, it's gone. Pull out an x from that x squared, I'm left with just a single x. On the last one, if I pull out a 2x, I'm left with 6y. That is the result of pulling out the GCF. Alright, so we look for anything that all the terms have in common. Okay. The next thing that you do is, actually, this is the easiest step to do, right? You count the terms. Oh, what do you mean count the terms? Well, counting the terms will help you decide what the next approach to use is. Okay. So, what does that tell you? If I count the terms and say I have 2 terms, then what do I know? Well, if 2 terms are there, the only way to factor it is to use a special factoring formula. Okay, and I'm going to give you 3 of them. One of them you'll have to know by heart. The other 2, if you ever need them, I'll provide them for you on the test, like say on the midterm. If you need them, For your homework or your quizzes, feel free to look back in your notes and have your notes out as you're taking those quizzes. Okay, so let's look at some of those special factoring formulas. The first factoring formula I want us to consider is what's called the difference of squares. What that means is that it's a difference of squares if you have two terms and they're subtracted. That's what difference means. And that each term is a perfect square. Okay, it doesn't have to just be a single thing squared. It could be something like 9x squared, right? Where both parts of it are themselves perfect squares. If it is a square minus a square, then it always factors into a plus b times a minus b, where a is that thing being squared in the first place, and b is that thing being squared in the second place. We also have a formula if it is a sum of perfect cubes. That is, if I can write it as something cubed plus something cubed, it is a plus b times a squared plus, actually minus, sorry, ab plus b squared. And you have a difference of cubes formula. That is a minus b times a squared plus ab plus b squared. You'll notice a very close similarity between the difference of cubes and the sum of cubes formula. Now, I did say one of these you need to know, and that is going to be this first one here. This one you should know by heart. That is, if you ever have two squares subtracted, a difference of squares, you should be able to factor that out into a plus b, a minus b, right? We'll do that, a couple of examples with that in just a second, but let me point this out. If you were to actually manually go in, just using the technique that we just learned how to do for multiplying, and multiply this out, you'll see, in fact, the right-hand side of each of these formulas, multiplied out, simplified, collect like terms, you will get the left-hand side. Okay, you get this. Notice, for example, in the difference of squares, if I were to multiply this out, I'd have a squared being the first. Notice what happens to the outside and the inside. The outside would be minus ab. The inside is plus AB. Minus AB plus AB cancels out and give me 0. That's why that middle term is gone. And then you multiply the lasts together and you have a minus b squared, which is exactly why this multiplies to give you a squared minus b squared. Now let me show you how you use that. Come down to this example here on part B. I have two things that I'm asked to factor. I've got a two-term or binomial that I'm asked to factor. I notice right away that they're both perfect squares. That is, I can write this as something squared minus something squared. In the second case, it's going to be a 2y that gives me 4y squared, right? The reason I write it like this is so I can identify the a and the b in the problem. A is x, b is 2y. So I can immediately write down that this factors into x plus 2y times x minus 2y. And there you go. That's it. It's factored. Right. By the way, let me point out again, the first step would have been to pull out the GCF, but looking at this problem, you see right away there's nothing in common of those two. So I jumped to the next step, which was to count the terms. There were two, so I knew I had to try one of my three factoring formulas. All right, let's see if we can identify where we might use a different factoring formula. Again, I notice on part B here that we have two terms, so I'm going to use a special factoring formula. I see the 3 here, which gives me, that's the clue, that's the hint, that's the identifying characteristic that lets you know these are going to be perfect cubes, and it's a sum. So I'm going to say, okay, can I write this as something cubed plus something cubed? And if I can, then I'll come back up and apply my sum of cubes formula. I can scroll up. I hope you don't mind me doing this real quick. My sum of cubes formula right here. Okay, now coming back down here, let me write this out. This is going to be x cubed, and this is going to be, what is it that's cubed that gives me 27? Well, that's a 3, because 3 times 3 times 3 is 27. Now, what cubed gives me y to the 9th? I have to remember that the way that I get, whenever I raise an exponent to a power, I have to multiply the exponents, right? If I had y squared cubed, that's y to the 6th, which wouldn't be enough, so that doesn't work. It has to be y cubed to get me to the y to the 9th. So that's why I'm going to put a y cubed inside here, identifying now that's my a and that's my b. Okay, so that formula said that this would be equal to, if I had a cubed plus b cubed, I'll just leave it up there on the screen like that. A cubed plus b cubed up here is going to be a plus b. So in my case, that gives me x plus 3y cubed times a squared, so that's x squared, minus a times b, so x times 3y cubed, I'll write that as 3xy cubed, and then plus the last term squared. Okay, I'm going to go ahead and write it down. I'm going to square 3y cubed, right? That's what's going to go right there. So I'll go ahead and work that out. 3 squared is 9. Y cubed squared, you multiply the exponents, is y to the 6th. There you go. That factors. And we're done. All right, so what do we do if we have now, instead of 2 terms, we have 3 terms? Well, what we're going to do is something that's called reverse FOIL. Now, there's a couple of different techniques for this. There's something called a grouping method, which I generally don't use. I know at least one of my colleagues in the math department chooses to teach that over this. This is kind of like a trial and error method. It's just the method that I use most often. What I will use as I teach this course as the way to factor a trinomial. So I'm going to walk you through how we do this reverse FOIL technique. Both techniques work. If you want to learn more about the grouping technique, feel free to access your online textbook and go through and find that in section in chapter 5 where they're factoring trinomials, and you'll see an explanation of how to do that. But for the purposes of this lecture, I'm going to show you just how to do the reverse FOIL technique. To do reverse FOIL, what we're trying to do is trying to reverse engineer the FOIL problem. Remember, the FOIL problem says that if I have 2 binomials multiplied together, I'll multiply the firsts together, the outside, the inside, and the last. So the first thing to notice is that this x squared term right here is going to be what I get if I multiply the first 2 terms together. That's the firsts. The result is x squared. So what do I have to multiply together to get x squared? Okay, the most natural choice would be x and x. The next thing that I look at is this sign right here. That plus sign. That gives me some information about what the signs are inside here. Right? If it's a plus right there, that means they're the same sign, right? Because the sign of that last term is going to be the sign that I get when I multiply the lasts together. To get a positive, they had to be the same sign, because when you multiply 2 numbers together, if they're both positive or both negative, you get a positive. Okay, so we got to figure out what sign goes in there. Now, what we do then is we look at the other sign to tell which. In this case, I have a plus sign right there. That means these are plus and plus. They're the same and they're both plus. Okay? Now, if that had been a minus, that means they're different signs, and you just put a plus and a minus in, and you decide which goes where based on the next step, which is the trial and error step. Okay, that last step, the trial and error step, is to identify what 2 things will add together on the outside to give me the 6x. So what I do is I take the 8 and I say, okay, what 2 things multiply together to give me 8? That would be 1 and 8. 2 and 4. Those are my only choices. So what I do is I come in and I put in a 1 and an 8, and I check the outside and the inside. The outside is 8x, the inside is 1x. I add those together, what do I get? 9x. Does that match the 6x? And it doesn't. So that means it can't be 1 and 8. I can rule that out. So now I need to come back with my eraser and delete what I just did. Got to take that out. It's definitely a reason why you should do this in pencil. So take this out, take this out, take this out. What's my other choice? 2 and 4. So I plug those in and see if it works. Okay, so outside gives me 4x. The inside gives me 2x. Add together gives me 6x. It checks. That means that is my polynomial factored. Okay. what you do is you go through and you exhaust all the possibilities on what choices you have to multiply together the first, to multiply together the last, and make sure and find the one that matches the middle term. If you exhaust all the possibilities and you don't find the one that matches, you have what's called a prime polynomial that does not factor. DNF is what I'd write, does not factor. But in this case, this one factors because we found a combination of firsts that multiply together and lasts that multiply together so that their insides match the middle term. So let's try this next one. Same idea. Now, what two things can multiply together to give me 3x squared? My only choice is 3x and x. Okay. Next, I check that sign. Right? What is the sign here? It's minus. So that means, like I said before, that they're going to be opposite inside. Now, you may ask, how do I know to put a plus here and a minus here? I don't. I just pick one. I could put a minus here and a plus here. When I start checking the middle terms, that will tell me whether or not I've got them in the right place. If I get the right number but the wrong sign, that tells me to just switch the signs. So now what about 72? What things multiply together to give me 72? All right, I'm going to start with some smaller numbers first and then work my way up to the bigger numbers. I know 8 times 9 is 72. I know 6 times 12 is 72. 4 times 18, yep, is 72, and I can do 3 goes into 72. What is it, 24 times, 2 goes in there 36 times, and 1 is 72. There's all my choices there. So what if I tried 8 and 9? What does that give me on the outside and the inside? That gives me a minus 27x and a plus 8x. Add that together, I get a minus 19x. Oh, looky there. I got lucky. I love it when I get lucky. I could have tried all these other ones first, but I got lucky and got the right answer. See how some of these problems can be rather lengthy. You'll not have a lot of lengthy ones in there, but I'm still not quite right. You see that? I've got a minus sign when I need a plus sign. That's where you go back and do what I told you before, where you change just those signs in the middle and make them the opposite of what they were, minus plus. That gives me a plus 27 and a minus 8. 27x minus 8x is positive 19x. So there we go. We have it factored. When there are 4 or more terms, we use a technique known as grouping, which means, in effect, we're going to group these into pairs or groups of a certain size and factor the GCF out of each one. There's not a GCF for the whole thing, but if I look at just the first two, there is something they have in common. They both have an x in common. Leaves me with x plus 2. The second terms, they both have a 4 in common. I'll leave that plus sign in between here, so plus. Pulling out a positive 4 leaves me x plus 2. And now here's the trick. This is when you know grouping works. Grouping works if you end up with the same binomial in both of the resulting terms. If that happens, you pull out that common polynomial. That is, pull the x plus 2 out front. And just like we've pulled out individual terms, we can now pull out binomials. What's left if I take an x plus 2 out of this? Well, I'm left with an x. Pull an x plus 2 out of this, I'm left with a plus 4, and that's it. That's how grouping works. It doesn't always fall out this way. If you try grouping one way, that is, I put the first two together and the last two together, and I don't end up with a common binomial, you might try grouping other ways until you've tried every possible grouping, and it may turn out, again, that you have a polynomial that does not factor using any of our techniques we've provided here. But this one is an example of what you will mostly see when you see 4 terms, and that's how we factor it. Now, the last thing that we need to talk about in this section is solving polynomial equations. That's one of the ultimate goals of college algebra, is we're going to come up with an equation that models something in the real world, and we want to solve it for that missing piece. The x, in all the stuff we've been talking about, when we start applying algebra, the x represents some quantity, some unknown or missing piece in a problem. So once you establish an equation that relates the unknowns together, you then have to figure out what is that missing piece. So that's the idea of solving an equation. Now hopefully by this point you know how to solve something simple like 3x plus 1 is equal to 10, right? If you wanted to solve that, you subtract 1 from both sides, you end up with 3x equals 9, then you divide by 3 both sides and you get x is equal to 3. Now if that blows your mind, if that's a little too advanced for you, then I can guarantee you're in the wrong class at this point and want to think about going back and taking our earlier class of intermediate algebra. But if this makes perfect sense to you, if you've done this and that's familiar to you, then you're ready to move on and talk about what happens if we have the squares. What if we have polynomials that have higher powers than just first powers in there? How do we solve polynomial equations? Okay, well, we use something called the zero factor property, which says that if I have two things multiplied together, we have an a and a b, and they multiply together to give me a 0. And now a and b could be anything. They could be polynomials, right? They could be like x plus 2 and x plus 4, like we saw up here in the previous example. But let's say they multiply together and you know it equals 0. Now what has to be true about a or b? Right? You can't multiply a 1 times a 1 and get 0, or you can't multiply any positive numbers times each other and get 0. It has to be that either the a is 0 or the b is 0. That's the only way that could be happening. Of course, they could both be 0, but one or the other or both has to be true. So using that property, we can now solve polynomial equations by 1. We get the whole thing equal to 0. We make it look like that equation right there. We get a 0 on one side. Then we factor it, and that's how we make it look like that left-hand side. Two things, or maybe several things, multiplied together equals 0. And then we get to say, okay, well, if it's equal to 0 and these things are multiplied together, we can set each factor equal to 0. So here's a good one. This example right here, the work is almost already done for us. It's polynomial, but it's already got it equal to 0 and two things multiplied together to give me 0. Okay, so that means to solve this, we've got to find an x that either makes the first one 0 or the second one 0. Now, just eyeball this thing for me. Look at this. What's the number in this first expression, or this first factor here, that I could plug in for x that would make that 0? Right? Clearly, I think everybody can see that that's going to be a 1. If I plug in a 1 in for x, that 1 minus 1 is going to give me a 0. And I don't care what happens to the other term, the other factor. I put a 1 in here, I get 3, but so what? 0 times anything is 0. So that tells me one of my solutions is going to be a 1. And another way to think of it is, set that equal to 0 and manually solve that by adding 1 to each side. You get x is equal to 1. Now, what about another solution? Is there another value that would make this whole left-hand side 0? Well, yeah, look at the second one. What about this x right here? All right, if I can find an x that says x plus 2 is 0, which I can by simply subtracting 2 from both sides, I get x is equal to negative 2. There is another value that if I plug in for x, it gives me a 0 here. It gives me something else here. In fact, it gives me like a negative 3. Again, I don't care, because one of those is equal to 0. Both of these are solutions to the original equation. All right, now looking at the next one. Same ball of wax, same deal, except that we've got to do a little bit of work ahead of time. We need to get the thing equal to 0. We see that it's a square and a first power term, which basically means that your technique for solving linear equations, that technique I showed you above where we just get x by itself, doesn't work anymore, because we can't ever get the x squared together with the x to make it just an x by itself, right? We can't isolate the x. So our only other option is to get it equal to 0 and then use our polynomial factoring technique. So to get it equal to 0, how do I get it equal to 0? Well, just move stuff. Throw things to the other side. We know we can add, say, 13x to both sides, and by doing that, that's going to give me a 0 on the right-hand side. Over here, I'll have 3x squared plus 15x plus 12. So now I'm going to factor. Now, you may want to jump to reverse FOIL, but let me warn you, first things first, right? What's the first thing you always try when you try factoring? And if you try it, it'll make your life a whole lot easier, right? Pull out the GCF. What do these three things have in common? They all have a 3, right? So pull the 3 out. I'm going to be left with x squared plus 5x plus 4 equals 0. Now I factor what's remaining. All right, that's going to be an x and an x. I know they're both plus, and 1 and 4 works, right? Because outside gives me 4x, inside gives me 1x. That adds together to give me 5x, so that factors. So now what I've got to do is set each factor equal to 0. Now I'm not going to set the 3 equal to 0, right? If I set 3 equal to 0, that doesn't make any sense, right? Because there's no variable in there. If I had pulled out a GCF with a variable, I would need to set it equal to 0. But in this case, I can't get anything out of 3 equals 0. It's not even true. So there's no solution that comes out of that factor. What about this one? X plus 1 equals 0. Yeah, subtract 1 from both sides. X is equal to negative 1. And this one, x plus 4 equals 0. Yeah, I can subtract 4 from both sides. X is equal to negative 4. Those are my two solutions. So that is how we solve polynomial equations. We're going to need to use that as we jump into Chapter 6. We're going to be having to factor all over the place. In fact, just about everything that we go through in Chapter 6, the very first step says factor. Factor, factor, factor. Okay? And then when we finally get to solving our functions in Chapter 6, we'll also have to come back and use this technique I just showed you here for solving equations that involve polynomials. And that ends the Chapter 5 review. We're ready to jump in to Chapter 6.